anytime they're attached to a variable, they just stick around as coefficients. But even with antiderivatives, the constants don't go away anymore. The constant actually picks up an x. We end up with more x's than we started with, not less. And so go ahead and do this one. So for each of these, just add 1 to the exponent, divide by the new exponent. Any of those coefficients are just going to stay the way they are. While you're doing that, I'll be right back. Okay, so what's the first term going to be?
10 over 8 x to the 8.
So 10x to the 10 stays, exponent goes up by 1, we divide by the new exponent. And we're just going to do that all the way across. So 5x to the 4th over 4 minus 3x squared over 2. And what about the 2 here? It's 2x plus c. Okay. Any questions about this? Okay. So then we saw at the very end, if we were given information about the derivative, this original function up here. So whenever we do antiderivatives, what's inside here is always some sort of rate. So like velocity or gallons per minute or something like that. So it's always some sort of rate that when we take the antiderivative of it, that's going to give us back the original function. So if this was a velocity function, this would be the position function. Because remember, the derivative of the position is velocity. So the antiderivative of velocity is going to be position. So the antiderivative is used to go in the opposite direction. And if we take the second derivative of the position function, first derivative is velocity, second derivative is acceleration. Well, if we start off with the acceleration function and take 2 antiderivatives, that'll get us back to the position function. And this is really important because acceleration is, in physics, force equals mass times acceleration. And so if we know what the forces are that are acting on an object, then we can figure out what its acceleration is at any given time. And if we know the acceleration, now we can use antiderivatives to get back to velocity, use another antiderivative to get back to position. So for instance, we know where all the planets are going to be 1,000,000 years from now, where in their orbit they'll be, because we understand the forces that are acting on them. And so we can predict where they're going to be at any given time. Does that make sense? Okay. And so the further we go, basically, this is all in preparation for differential equations, because differential equations solves problems like that. That's the ultimate goal of where we're trying to get to, is differential equations describe the universe, and we need to what we're learning now are the tools to solve differential equations. Okay? Okay. And we also saw that if we know what the, if we're given the f prime here, if we're given a value, we can use that value to find c, and that's called an initial value problem. So if I said, if this is our f prime of x, and I said f, say we have that f of x, sorry, f of okay. So say f of 1 equals 5. We're just given this extra piece of information. How can we use this extra piece of information to find the value for c? So if this is our f of x, what do we do? We just plug it in, and so when we plug it in, that's going to get rid of all of our x's. It's just going to leave us a c and some numbers. And so then what we're going to do is just set that equal to 5. So this is going to be 10 over 8 times 1 to the 8th, 5 times 1 to the 4th over 4, minus 3 times 1 squared over 2, plus 2 times 1, plus c, and we know that this needs to equal 5. And now from here we can figure out what c is. So are we okay with that? Okay. And that was really basically all of 4.9. Actually, it's half of 5.4 as well, because 5.4 is where they actually introduced this notation for antiderivatives. And so we're actually a little bit ahead of where we normally would be. So I kind of mix up 4.9 and 5.4 together there. Okay, any questions about this?
So then what happens to the 5?
So now we just solve for c, we subtract this off the other side. And so we're going to get minus 10 over 8, minus 5 over 4, plus 3 over 2, minus 2.
If we have just brought...
We could have brought the 5 that way and the c this way.
Yeah.
Would have worked too, yeah. Instead of moving all of this piece, just swap these two
Yeah.
and arrived at the same result. Okay. So c equals, let's see, so this is negative 5 over 4, and that's negative 5 over 4, plus 6 over 4. So let's see. We have negative 5 over 4, negative 10 over 4, negative 4 over 4, 8 over 4, 2 over 4. Okay. So adding these all together, this is what we get. 1/2. And so now that we know what c is, we can just replace the c with 1/2. Okay. And so now we have our function. And this is called an initial value problem. When you're given this extra piece of information here, you can use that to figure out what c is. Okay. Any questions here? But the important thing to remember is if we apply this to the velocity, we're going to get position. And that's it for 4.9. Okay? Any questions?
You say we're going to get the velocity?
If we start with the velocity, we can use the antiderivative to get position. So this is velocity. This is velocity.
Yeah.
This is position.
Okay.
So this is how fast it's moving, this is where it is.
Okay.
Okay. Okay. Any questions? Okay. So yeah.
Sorry, what did you say about the acceleration again? How do we get there?
So if we started with acceleration, so here we have, so f of t, if this is position, f prime of t is velocity, double prime of t is acceleration. And so taking derivatives takes us down the list, antiderivatives take us back up the list. Okay. Okay. So now what we're going to do is we're going to move on to 5.1. And 5.1 is doing something completely unrelated to this, or at least seemingly unrelated to this. It is going to tie back together in the end, but for now it's going to look like it's something completely different. Yes?
What are the units that are on the exam with me on Wednesday?
What is it? Oh, what sections? So the exam is 3.9, 4.1 through 4.4, and 4.7. So what's that?
Thank you.
So 3.9 is the related rates. 4.7 is the optimization, and then 4.1 is finding maxes and mins. 4.2 is the mean value theorem. That's not going to be on there. There's nothing from 4.2 on there. 4.3 is sketching the curves, the increasing, decreasing, concave up, concave down, and 4.4 is L'Hopital's rule. All right, so what we're going to talk about next are areas. So we're going to look at finding the area of regions in the plane. Okay. And so if we have a function say we have a function and we have 2 points on the x-axis, A and B, and our goal is to find the area of that region. The region bounded on the top by the curve, on the bottom by the x-axis, on the left by A, and on the right by B. So we want to find the area of that. Okay. The problem is we know how to find areas of polygons. If our shape has all straight sides, we can always find the area of it just by slicing it into triangles and using the formula for the area of a triangle. But the problem is because we have this curve on the top, we can't do that. We can't find the area of this exactly. Okay? But what we can do is we can approximate. We can get close to the area by doing something like this. I'm going to take this, I'm going to divide it, slice it into regions like this. Okay. And now what I'm going to do is I'm going to just chop off the top of these and make them flat. Okay. So what I'm going to do here is I'm going to find the area of the red rectangles there. Is that going to be exactly the area underneath the curve? No. Will it be close?
Yeah.
Yeah, it'll be pretty close. The rectangles stay pretty close to the curve. And this one's kind of nice too, because here we lose a little bit of area because the rectangle's below the curve. But then here we pick up some extra area, and those kind of cancel each other out, not perfectly. Now we do have a few extra over there. So in this case, it'd probably be a little bit too high. Does everybody see how that works? And we can find the area of these rectangles. Okay? And so what we have here, so let's call these points x0, x1, x2, all the way out to x n minus 1, and xn. Okay?
What is it, -1?
So n is the last one.
Uh-huh.
So the n minus 1 is just the one before it. Okay. Now, looking at this, the height of each rectangle is based off where it's touching the curve, right? And so the height here, this is f of x0 because it's touching the curve at x0. F of x1, and so on, all the way down to f of x in minus 1. But one thing that we want to note here is it's not touching the curve at xn. None of the rectangles touch the curve there. So we're never going to have a rectangle that's the height of this one. Does everybody see that?
You have a little, is that why you have a little gap in there?
Well, I mean it here?
Yeah.
No, it's just my pin.
Why is it not touching it?
So it's anchored at this side of the rectangle.
Yeah.
When it goes straight across,
I
it
see.
misses the curve.
Okay.
Okay. And so every one of my rectangles is anchored on the left side of, it's touching the curve on the left side, not on the right side. Okay. Okay. Now the other thing is, so the height, we know that we now have a bead on the height of each of the rectangles. What about the width of the rectangles? That distance from there to there. Okay. Now we're going to give this a name. First off, we're going to assume that these are all equally spaced. We're going to call this is the Greek letter delta. We're going to call this delta x. Okay, and delta x is just telling us what is the width of each one of these rectangles. But we can calculate the width of each of these rectangles. So first off, what's the total distance all the way across? Say this is at 2, and that's at 10. How far across is that?
8.
How'd you get that?
Add it together.
So from 2 to 10?
Yeah.
Not adding, it's not 2 plus 10. It's 10 minus 2, right? Well, if we're going from A to B, what's the distance across that going to be? B minus A. Okay, if you want to know the distance from a start to an end, you always do the end minus the start. Okay, so if this was 2, that was 10, we would do 10 minus 2 gives us 8.
2 because it's off?
Well, yeah, I mean, I was just as an example.
Okay.
So, so it's hard to, when you're working with variables like this, it's hard to recognize that it's B minus A, but if I gave you numbers, actual numbers here, you can figure it out just intuitively. You'll just know that if it's 2 to 10, that's a distance of 8 because it's 10 minus 2. Okay, so delta x is going to be B minus A. B minus A is the distance all the way across, but we're dividing this into n rectangles. Okay, so one rectangle, 2, 3, 4, all the way out to n rectangles. So if the entire distance is B minus A, what's the distance of each one of the rectangles?
B minus A divided by 5.
Divided by, well, however many rectangles there are. So in my picture there were 5, but in general we don't know how many there are. Okay? And so now we want to find the area of, the total area of all of this. Okay? Okay. So our area, when you make a wavy equal sign like that, means approximately equal to. This first rectangle is going to be a height of f of x0 and a width of delta x. Next rectangle is f of x1 delta x, f of x2 delta x. And we go all the way out to f of x n minus 1 delta x. Okay.
What's the n?
Under the number of.
N is the number of rectangles.
Oh,
how many
Oh.
rectangles. So in my picture, it's 5, but
Yeah.
but we're gonna do this with lots of rectangles.
Okay.
Okay. Everybody okay with this? Why don't we have f of x in delta x at the end of this?
It's not included.
Because it's not included. So the rectangle, that last rectangle doesn't touch the curve there. So since it's not touching the curve at that last point, we're not going to include it in our list. Does that make sense, everybody? Okay. This is called the left-hand rule
Because it's only touching from the left.
because it's only touching on the left. We're going to follow this up with the right-hand rule, which is going to redraw the rectangle to put them touching on the right.
So then if it's touching from the right, then it only would be touching from the right, not from the left?
Yes, exactly. Okay. Now we can clean this up a little bit. Notice that every single term has a delta x in it. So we can factor that out.
Why are you adding the dots? on
The
there?
dots are just, these are all the extra terms in between. So 1, 2, 3, dot, 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 out to 15 or 16 or 30 or however many we have. Okay, so we can factor out that delta x and then and do that. So basically what's happening here is we're just adding up all the function values and then multiplying by delta x after we're done. Okay.
So when do we divide by the number?
Well, the number, this is how we find delta x in the first place, is this.
Oh, I see,
And that's the delta x that goes in that position.
I see.
Okay. So let's look at an example. So f of x equals x squared. We want to go from 1 to 3 with n equals 4. So this is our region. And we're dividing this into 4 rectangles. And it's going to look like this.
So then is that gonna touch from the row?
These are all touching the curve on the left corner.
I thought because maybe it's going the.
Yeah,
curve.
for the left-hand rule, it doesn't matter if it's going up, going down. It's always touching on the left edge. Okay. So first off, what is our delta x?
It's the same, B minus A, right?
B minus a over n, but we have values for b, a, b, and n. So what is b?
3.
B is the endpoint on this side. A is the endpoint on this side. And what is our n?
By 4.
It's 4. Which equals 1 half. Okay? Okay, so since our n is 1 half, we can mark off the values for these points. Just add a half, add a half, add a half, add a half, and that gets us all the way to the end. Okay? And so what we're going to get is, so looking here, what are the values of the function that we're going to be plugging in? Where is the rectangle, at what points are the rectangles actually touching the curve? There's 4 points that it's doing.
2.5.
so at x equals 1, it's touching the curve.
1.5.
1.5, 2, 2.5. Are any rectangles touching at 3?
No.
Okay, so our area is going to be approximately equal to delta x times f of 1, f of 1.5, f of 2, f of 2.5. Okay, does everybody see that?
And are we always gonna be given?
We will always be given the function, we will be given our endpoints and a total value for n. Okay. Okay, since our function's x squared, we just plug those values into there. And so this is going to come out to 1.5 squared is 2.25, 2 squared is 4, and 2.5 squared is 6.25. And that comes out to 6.75. Yeah.
Will we have like what is it, like centimeters or?
So the units, if the units were given, we could attach the units to it. For the problems in 5.1, they never give any units for them. They just say, just find that area. So, and the problem with attaching units to it now is we don't really know what this function's referring to at this point. So typically, they just don't have units on these. But in reality, if we knew what this function was telling us, what the units were on that function, what the units are on the x-axis, what the units are on the y-axis, we could attach units to this.
What happened to the last calculator, the 13.5?
So it just, well, 13.5 is adding those up.
Yeah.
And then we multiply by a half to get 6.7.
Oh.
Okay. Any questions? Okay, so what I want to do is show you on the calculator a really quick and easy way of getting these values. So when we want to do these, just immediately we can get a list of these values here in basically 1 or 2 steps on the calculator. No matter how many values we need, we can do it really quickly. And this is going to be using the table feature on the calculator.
Do you have extra calculator?
Do I have extra calculators? I can get some calculators.
Do you have a lot of work with the calculators or just this?
Just this.
Okay, then I don't need it. I
Okay.
brought mine in the car.
So this, there's not going to be any of this stuff on the final. None of this area stuff is going to end up on the final. This is just for the homework. There's a few problems. There's not even that many of them. But I do want to show you how to do this. And it's kind of nifty too. So what we're going to do is we're going to go to y equals and we're going to type in our functions. Let me pull this down. Okay. So we're going to type in the function. probably set right now, yours is probably set up because this is what we've been using it when we did limits. It was probably set up to ask, so when you go to table, it'll be empty. And from here, you can just type in the values that we need. 1, 1.5, 2, 2.5, and we get all the function values right away. You don't need to show any work on getting function values, just use the calculator to do it, but we can get all of them that we need really quick. Everybody okay with that? Okay. Now there's another trick that can do it even better. The calculator can do all of them automatically, you don't even have to type them in. If you go back to the table set here and change this to auto, it'll automatically populate the X values. The only thing you need to tell it is where do we start and what is our what's our step? Is it so this they call it delta table, we call this delta X. Okay, so our interval was 1 to 3, and we got delta X was 1/2. So we're going to tell it to start at 1. We're going to start at this value and do delta X equal 1/2. Okay, now when I go back to table, now when I go back to the table, it's just automatically going to populate it. Now it doesn't know where to stop, so it just does as many as you can see on the screen. We know that we only need the first 4 of them. Okay, so you have to know where to stop on this. You never want to go past. You never want to go past this value. So, but in this case, in the left-hand rule, we don't even want to touch that value. We want to stop before we get to that value, 2.9. Is everybody okay with that? Okay. So that's how we do that on the calculator. Okay, and this is called the left-hand rule. And the notation for it is L sub n. That's what this, we would label this. Our left-hand rule gave us 6.75, so that's L sub n. L sub, in this case, n was 4, so we would say that this is L4. Okay, so in the homework, it's going to say find L7 or L32 or whatever. That is telling you what your value for n is. Okay. And this formula is delta x, f of x0, f of x1, all the way out to f of x n minus 1, but not f of x n. We leave that one off. Oh, and delta x is b minus a over n. We also want the right-hand rule which is r sub n, and let's see how this changes things. If we start anchoring our rectangles on the right side instead of the left side. Okay, I'm going to do these in green. Yes?
I have a question. Why does it start like x0, x1, x2, and then it changes to xn minus 1?
So this formula, I need to write a formula that's going to work no matter what n is. So I can't list every single one of them. So in our problem, n was 4, so it would just be 1, 2, 3, 4.
Oh, okay.
But if n was 8, it would be 1, 2, 3, 4, 5, 6, 7, 8. That dot, dot,
It's a
dot.
sequence.
It's a sequence, yeah. The dot, dot, dot just means whatever needs to be in between.
Okay.
Okay? Okay, so let's go back to this picture and let's figure out the right-hand rule instead. All of my anchors are gonna be on the right side of the rectangles instead of the left.
And so how would we know will it tell us if it's an RN or LN?
Yep,
then?
it'll say RN or it'll say LN, so R4 or L4, and you'll know which one is which one you do. Most problems it'll say find L4 and R4. It'll ask you to find both of them on pretty much every problem. So, okay, so now looking at this, looking at the green, ignore the red. Which values down here is it touching the curve at? The green ones. Is it touching at x0? Is the green on the curve above x0? No, it
Yes.
misses it. So the green up here is above the curve.
Oh, I see, no.
But at x1, this rectangle's touching it. x2, x3, x4, and in this case, it's touching it at the very last one as well.
Right.
Okay, so our right-hand rule is going to not include x0, but it will include the last one that's missing here, and everything in between. Okay, so this is going to be, and our delta x is the same. The widths of the rectangles didn't change at all. And we get this. Okay. Is everybody okay with that? So let's go back to this problem and figure out R sub n. Okay, so we're gonna do delta x. And now what values, if we're doing the right-hand rule, what values are we gonna use off of the x-axis here? So if for the left-hand rule, we skip the last one. For the right-hand rule, which one do we skip?
One,
We skipped the first one and used the rest of them, right?
including the three, right?
Including the 3 this time. So this is going to be f of 1.5, f of 2, f of 2.5, and f of 3.
So for the RN, you don't have the N minus one.
Well, the n minus 1 is in here. It's just part of the dot, dot, dot now.
I see.
Okay. And so this is 1/2. And the function values, we already have all the function values except for the very last one, but that last one is just going to be 3 squared is 9. So this is going to be 1.5, 4, 6.25, and 9.
How did you?
Sorry, 1.25.
Oh, the 3 squared? You got the nine?
Yeah, the 3 squared is
I see.
2.25. So it's just these values here, except for the 1 on the front is left off, and we get a 9 at the end. Okay, and so it's going to be 6, 12, 21, 25. This whole thing comes out to 10.75. So this first one, 6.75, the red rectangles, is that too high or too low of an approximation?
It's too low.
The red ones are too low, right? What about the green ones though, if we anchor them on the right side?
Too high.
Too high.
That's too high. So the actual area is somewhere between 10.75 and 6.75. This is pretty common that the left-hand rule and the right-hand rule usually are the error is in opposite directions. One's too high, the other's too low. One trick to getting to be more accurate is just take the average of these two. is considerably more accurate than either one of them by themselves.
So add them together and divide them?
Add them together,
By two.
divide by 2. We'll do we'll be closer to the right answer. Still won't be exact, but it'll be a lot closer than either of these two numbers.
Is that kind of like how you were doing the epsilon and delta?
Kind of. It's kind of like the epsilon delta stuff. It's has some amount of error to it. We don't know exactly what that error is, though, is the problem. So, and we don't have at this point, we don't have an easy way to find out what that error is. We will be able to determine exactly what that area is by the time we get to 5.3. Okay. Any questions about this? Okay, so these are the formulas for the left-hand rule and the right-hand rule. So let me give you one to do. So here's our function, f of x equals 3x minus 1. We're going from 2 to 6, and we want to find L4 and R4. Okay, so let's kind of go back through the steps of what we did here. First thing we did was we found delta x using the b minus a over n. Then I drew the picture and marked off the values on the number line there. Okay, so our function here is going to look like this. Okay, so this is what our function looks like. And now what you need to do is figure out what your delta x is, mark off the values, add delta x, add delta x, add delta x until we get all the way to 6. Mark off those rectangles and anchor them on the left side for L4, anchor them on the right side for R4.
This would be interesting, right? Because
So what do you guys get for delta x?
delta x is 6 minus 2 over 4. So then 4,
Okay, is everybody okay with that for delta x? Okay, so now what we want to do is we want to mark off on the number line what those values are going to be. Okay, so we're going to do 2, we're starting at 2, and we're just going to keep adding this value. So when we divide this into 4 rectangles,
3.
plus 1 is 3, 4, 5. And typically the book is pretty nice about, the problems give you, are pretty nice about choosing values for n and intervals that make it not too messy. Sometimes you do get fractions, but usually they're just halves. You did something like n equals 7, then you get these really messy decimals in between, so they tend to be kind of nice to you. So those are the values there. For the left-hand rule, which 4 are we going to take?
2, 4,
2, 3, 4, 5 for the left-hand rule. For the right-hand rule, which ones are we going to take?
3, 3, 4, 5, 6.
3, 4, 5, 6. So we're just going to find the left-hand rule is going to be delta x, f of 2, f of 3, f of 4, f of 5. And for R4, it's going to be delta x, f of 3, f of 4, f of 5, f of 6. Okay, and only thing you have left to do is just take these values and plug them into the function. And replace them here, add them up, and
How come over here you wrote the approximate?
so this is the area,
Yeah,
is approximately equal to this.
yeah.
L4 and R4 are exactly equal to those values. The area is approximately equal to these. But when we say L4 and R4, we're saying this is the formula. This is L4, which is approximately equal to the area. So this is going to, what I'm going to say here, this is approximately equal to the area. Does that make sense to everybody?
I guess what I was asking is you have 1/2 here, right? And then why not just put 1 over there?
We are. I just didn't put it here. But that's what, this is going to get replaced with 1. Those are going to get replaced with whatever that you get when you plug them into the function. So this is going to equal 1. Okay, so when we plug in 2, we're going to get 6 minus 1 is 5, plus 8, plus 11, plus 14. So just plugging those values into the function, those are what we get. And so this is going to come out to 13, 24, 38.
You're skipping a little step, right? You're just saying, so 3 times 2, right? Is what you're saying?
So
Then
3, yeah,
2
so
minus
3
1.
times 2 minus 1, that gives us 5.
Okay.
Since the calculator does all these for me, I'm not going to like show plugging them in there. For you, just use the calculator. Just put this as your y equals. Go to the table. Plug in those values. You can have it set it to auto if you want, or you can just do it manually and type in 2, 3, 4, and 5, and then just replace the numbers there. Okay, and so here we're going to get 1 times 8 plus 11 plus 14 plus 17. Let's see, that's 31, 42, 50. Okay. And so those are our left-hand rule and our right-hand rule. Okay. Any Any questions here? So these aren't very accurate in actuality. So the actual value is going to be somewhere in between those two. Now we can get more accurate by adding those two together and dividing by 2. But what's another way we could get more accurate with these values? Yeah.
Adding more rectangles.
The more rectangles we use, the closer the approximation is going to be. Okay? Well, if we make millions of rectangles in between here, then our error is going to be so small, because every tiny rectangle, the curve's not going to change very much in that little tiny window. Okay? So the actual area is going to be the limit as n goes to infinity of L sub n. Or R sub n, either one. Both of them are going to be coming at it from opposite sides. But ultimately, this is what we want to do, is we want to take the number of rectangles and just take the limit as n goes to infinity. Yeah?
Question, are those lines in there? You have, so 8 plus 1,
8,
Is there a
so
line?
5 plus 8 plus, it's 11.
is it what?
11.
11. Oh, 11, I'm sorry.
Yeah. It looks kind of weird because the pluses and then the 11 in there. All right. So ultimately, this is what we want to do, is we want to take the limit as n goes to infinity. Okay. 5.2 goes into how to do these limits, but it does it in a way that immediately is going to get replaced in 5.3. So 5.2 does it in a very complicated, messy way. Immediately in 5.3, it gets replaced. And so I'm not even going to bother doing that in 5.2. So we skip over pretty much all of 5.2, except for the notation that's going to be involved here. So 5.2 introduces the notation for how to denote this, what's going on here. And so that's the only thing out of 5.2 that we're gonna work on, because they do it manually, and then 5.3 would get replaced with a much better way of doing it. So, okay, but any questions here? Okay, so let's look at an application of this. Why would we want to know these areas? Okay. So suppose we're driving our car. We're driving our car, and our car has a speedometer, so we know at any given point in time exactly how fast we're going, right? And suppose we have a stopwatch, and we start that stopwatch at 0, and we look at our velocity at that moment in time. So say at time 0, we are going 25, and we're going to say this is in feet per second. For some reason, we have a car that gives us our speed in feet per second instead of miles per hour. Really, we would just have to, we could convert it to feet per second, but I'm just going to give it to you in feet per second to begin with here. So, okay, so suppose we're going 25 feet per second at 0. When the stopwatch hits 5, say we're going 35 feet per second. At 10, say we're going 42. 15, 49, 20, maybe we come back down, oops, we come back down to 45, 25, we're going 40, and 30, we're going back to the 30. Okay. So if we graph this, so 5, 10, 15, 20, 25,
Why is it decreasing as it goes down?
Well, sometimes you go faster, sometimes you go slower.
Oh,
Okay. And so I'm gonna plot these points. At time 0, we're going 25 miles per hour. Then at 5, so this is 5, 10, 15, 20, 25, 30, 35, 42, 49, 45, 40, and 30. Okay, is everybody okay with that? And our actual velocity would probably look something like this if we filled in, kind of would look something like that maybe. Okay? So this is time. This is the velocity. Okay. Well, if we know how fast we're going, we should be able to figure out how far we went, right? And we know the relationship between distance and rate, that distance equals rate times time. But let's do something here. Let's take this and make the assumption, instead of following the actual curve, let's make the assumption that between 0 and 5, we were stuck at exactly 25 feet per second the entire time. So instead of increasing gradually, what we're going to end up with is these big jumps. Okay?
so is that start touching from the left and the right?
So these are, well, no, they're all anchored on the left. Okay?
Because there was a point over there too.
Right, but the rectangle doesn't touch there.
I see.
The rectangle, it passes through there, but it doesn't touch the corner. It's not anchored there. Okay. But now let's look at what we have here. So this rectangle, from here to here, that's time. That's the amount of time to go from 0 seconds to 5 seconds. Right? And the height, this way, that is just the rate. Okay? Which means the distance, which is rate times time, is exactly the same as the area of that rectangle. Does that make sense, everybody? Well, this rectangle is the distance that we traveled in the first 5 seconds. This is the distance in the next 5 seconds. Next 5, next 5, next 5, next 5, all the way to the end. Which means if we add up the area of all of those rectangles, that will be how far we traveled, total. Okay? Yes?
Why sometimes you have, you go over the curve and sometimes you stick a little bit?
Okay, so I just want to make sure that all of my rectangles are anchored on the left side of every rectangle where they touch the curve. Now here, when I touch it on the left side, it stays under the curve because the curve's going up above it. Here, when I've anchored on the left side, the curve stays below it because the curve's coming down. So the direction that the curve is going determines whether my rectangle is going to be above or below.
Okay.
But I always want it to touch on the left side. If I'm doing the left hand
Yeah.
rule. If I want to do the right hand rule, I would reverse all of those.
Oh,
Okay, so the distance is going to be, now this isn't going to be exact because we're not going exactly 25 feet per second for that entire time. That's not how we drive. We don't stay at a constant speed and then immediately jump up to the new speed, which is what the red rectangles are telling us we're doing. But in reality, we're doing a gradual increase probably.
Yeah.
So when we calculate the area, we're not gonna be exact, it's gonna be an approximation. Okay? And so our distance traveled is gonna be approximately equal to, let's add up all of those rectangles. So this is going to be a rate of 25 on the first rectangle and a width of 5. So that delta t is 5. That's how wide all of those rectangles are. Plus, the next one has a height of 35 and a width of 5. Plus a height of 42 and a width of 5. A height of 49, a width of 5, a height of 40, and a width of 5. Oh, and that's where we stop. Notice that the rectangle doesn't touch at 30, so we don't ever actually use this value. So none of the rectangles are that high. So there should be 6 of them. So there's 1, 2, 3, 4, 5, 6 rectangles. 1, 2, 3, 4, 5. Did I leave something off? 25, 35, 42, 40. Oh, I did. This is 45 times 5 and 40.
So with the width, it doesn't increase no matter what.
Yeah, so it's because the width is determined by how far apart the t values are. And so in this case, they're all a width of 5. Okay? And so our approximate distance is going to be whatever we get when we have these. If someone with a calculator want to do that real quick. If you want, you can add these together. Just add those numbers up and then multiply by 5 after you're done. $1,180. Okay, and that's our distance traveled. That's going to be measured in feet. And actually, if we look at the units, so go back to your question about the units, the speed is measured in feet per second. That's our rate. So this is feet per second. That's second. So the seconds, so we have feet per second times second, and what happens is those end up canceling and we're just left with feet at the end. Okay, and so this is where the units come into play. For this to work, this has to be given to us as a rate, like feet per second, or gallons per minute, or whatever the rate happens to be.
Is this gonna be on the exam?
This is not gonna be on the exam.
On the final?
Not on the final. It's just homework on this. Because we're gonna do a much better way of finding these areas in 5.3. That 5.3 and later is definitely gonna be on the final. Okay, so here, let's look at what happened. We were given velocity, right? We found distance traveled, which is which is essentially just where are we? If we start here and we travel 1,180 feet, it's gonna tell me where I am at the end, right? This process of finding the areas turned velocity into position. What operation turns velocity into position? How do we, if I gave you a position function, how would you turn that into a velocity function? Take the derivative. How do we turn velocity back into position? Antiderivative. So these areas that we're finding are really just antiderivatives. Okay? So it seemed like we switched to 5.1 and it became very disconnected what we just did in 4.9, but it turns out that it's exactly the same thing. Not quite exactly the same thing, because this isn't telling me where we are, this is telling me how far we traveled, okay? And so if we traveled 1,180 feet, it depends on where I started. If I start here and travel that far, I'm gonna end up in a different place than if I start here and travel that far. Does that make sense, everybody? That's where the plus C comes into play. Because that plus C is kind of where do you start type of thing. So it's not exactly the antiderivative, but it's really, really closely related to it. And the antiderivatives are going to allow us to find these areas very quickly and very easily. Okay? Any questions about this? So this is the connection between 4.9 with the antiderivatives and 5.1 with the areas, because the antiderivatives are going to tell us the area. Okay, so that's it for 5.1. So let's go ahead and take a 10-minute break. We're going to come back and 5.2, just really quickly introduce the notation for this whole area stuff. It's going to be very similar to antiderivatives because we know they're related now. And then in 5.3, we're going to talk about how to actually calculate them. We'll probably get a little bit into that even today. So 5.2 will go really quickly, but 5.3